Our next lesson in the module on counting or combinatorics will be a lesson on permutations. A number of the applications of the rule of products that we learned in the last lecture are of a specific type, and because of their frequent appearance, they're given their own designation. These are called permutations. We already saw a couple examples of this, we just didn't call them permutations. So let's see a couple more examples. For example, ordering the elements of a set. How many different ways can we order the three elements of the set A equal to A, B, and C? Since we have three choices for position 1, two choices for position 2, and one choice for the third position, by the rule of products we have 3 times 2 times 1 equal to 6 different ways of ordering the three letters. And we can illustrate that with a tree diagram. Or how about ordering a schedule? A student is taking 5 courses in the fall. How many different ways can the 5 courses be listed? And then there will be 5 times 4 times 3 times 2 times 1 equal to 120 different permutations of the set of the courses. So in each of the above examples where we use the rule of products, we'll note that we were asked to order or arrange elements from a single set, and each element is listed exactly once in each list. This is called a permutation. So if there are n choices for position 1, then there will be n minus 1 choices for position 2, n minus 2 choices for position 3, and so on. Another example might be orderings of the roster for a baseball team. The alphabetical ordering of the players is one permutation. Other orderings might be done by batting average, maybe age or height. The information that would determine the specific ordering would be called the key, and we would expect that each key would give a different permutation of the names. If there are 25 players on the team, then there are 25 times 24 times 23 and so on, times 3 times 2 times 1, different permutations of the players. And that's a huge number. You can see it written out here, and it's so long that I can't even properly pronounce it. But writing it in this form, all of the digits written out like that, is not particularly instructive or informative. On the other hand, leaving it as the product 25 times 24 times 23, as it's written here, actually tells you more about the number and where it comes from. So this is where we'll introduce the notion of factorials, which we again sort of talked about briefly in the previous lecture. If n is a positive integer, then n factorial is the product of the first n positive integers, and we'll denote it with the exclamation point. Additionally, for convention, we'll define the 0 factorial to be 1. So this is important to remember because it'll come up from time to time. 0 factorial is just 1 by definition. So the first few factorials can be seen here. 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6, because it's 3 times 2 times 1. 4 factorial is 24, and so on. One other important thing to notice is that 4 factorial is 4 times 3 factorial. And 5 factorial is 5 times 4 factorial. And these numbers grow extremely quickly. 5 factorial is only 120, but by the time we get to 11 factorial, we already have, it looks like 39 million and something. So if the answer to a problem happens to be 25 factorial, and we know it's that huge number that we saw before, we would never be expected to write the huge number. You would just leave it as 25 factorial, and you would denote that by 25 with the exclamation point. However, It's fairly common that the answer to a problem might be a ratio of factorials or a factorial divided by a factorial, like you see here. So if you have 25 factorial divided by 23 factorial, well, it's going to look like 25 times 24 times 23 times 22 dot 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 times 3 times 2 times 1. And then on the bottom, you have 23 times 22 times 21 times dot 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 3 times 2 times 1. So clearly, these will all cancel. 1 cancels with 1, 2 cancels with 2, 3 cancels with 3. 21 would cancel with 21, 22 cancels with 22, 23 cancels with 23. So something like 25 factorial divided by 23 factorial ends up just being 25 times 24, which is 600. So if you have fractions involving factorials, you can often reduce them that way, and you would be expected to do so. If the set A has the cardinality n, then there will be n factorial ways of permuting the elements of A. So just like in the example A, B, C that we had before, there were 6 ways because the cardinality was 3, so there were 3 factorial ways. But you may want to know how many ways to permute a subset of the elements. So maybe k elements out of a set of n objects, where k is a positive integer less than or equal to n. An example would be a club of 25 members holding an election for president, secretary, and treasurer in that order. Then assume a person can hold only one position. How many ways are there of choosing the 3 officers? By the rule of products, we have 25 ways for choosing the president, then 24 ways for choosing the secretary, 23 ways for choosing the treasurer. So this brings us to the formal definition of a permutation: an ordered arrangement of k elements selected from a set of n elements where k and n are both greater than or equal to 0, and k is less than or equal to n. Where no 2 elements of the arrangement are the same is called a permutation of n objects taken k at a time. And we'll often denote it here, p, and then in parentheses n comma k. And there's a counting formula for permutations. The number of possible permutations of k elements taken from a set of n elements, which again is denoted p and in parentheses n comma k, well, it's going to be n times n minus 1 times n minus 2, all the way up to n minus k minus 1. So this is, n minus k minus 1, and then we distributed that minus. That's why it looks like n minus k plus 1. And the notation for a product, just like we know our notation for sums is using sigma, this would mean adding them all up if I use the sigma. If I use this big pi symbol, that means the product. So this product here can be written more compactly just as this product. Or another nice way of representing it is as this fraction of factorials. Just like we saw up here, we get a lot of cancellations when we do this. So another way of writing this product, n multiplied with n minus 1 all the way down to n minus k plus 1, would be to say it's n factorial, and then I divided by n minus k factorial. So here's the proof of the fact. If k is equal to n, meaning we're permuting n elements from a set of n elements, then our permutation formula would be n factorial divided by n minus n factorial, or n factorial divided by 0 factorial, which is n factorial divided by 1, which is n factorial. Otherwise, if k is strictly less than n, then the first position can be filled by any one of n elements, the second position by n minus 1 elements, the kth position by any one of n minus k minus 1 elements. So hence we get this form by rule of products. And it's an important note to make that this was derived solely by using the rule of products. So just like we said at the introduction of this lesson, the permutations are really just a special case of the rule of products. Here's another example, choosing officers. A club has 8 members eligible to serve as president, vice president, and treasurer. How many ways are there of choosing? So using the rule of products, we would say that there are 8 choices for the president, then 7 for the vice president, and 6 for the treasurer, assuming that no one person could hold more than one office. And by rule of products, then we have 8 times 7 times 6 equal to 336 ways. If we directly used the permutation formula, then we would want 3 officers from a set of 8 possible members. That would be 8 factorial divided by 8 minus 3 factorial. 8 minus 3 factorial, of course, is 5 factorial, so this is 8 factorial divided by 5 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. So doing my cancellation, I clearly get that it's 8 times 7 times 6, the same number. So these are the same method, and it's often just going to be a little faster and easier to think of it this way. Revisiting the previous example of ordering the courses, to count the number of ways to order 5 courses, we could still use the permutation formula. We want to know the number of permutations of 5 courses, taken 5 at a time. So plugging into our formula, that would be 5 factorial divided by 5 minus 5 factorial, which is 5 factorial over 0 factorial, or 5 factorial over 1, which is 5 factorial. Now how about different conditions that we could impose? Consider only the digits 1, 2, 3, 4, and 5. We could be asked, how many 3-digit numbers can be formed if no repetition of the digits can occur? So this is a permutation. So you can see solutions to A, solution 1, and solution 2. We could either use the rule of products to think of it as 5 choices for the first, then 4 choices for the next, then 3 choices for the next. Or we could use our permutation formula, and we'll get the same answer either way. The second part of the question says, how many 3-digit numbers can be formed if repetition of digits is allowed? Well, the definition of a permutation indicates that no 2 elements in each list are the same. So the permutation formula we cannot use here. However, we can still just apply the rule of products. And we'll have 5 choices for the first digit. We'll have 5 choices for the second digit and 5 choices for the third. So this just gives us 125 possibilities. And then the third part of the question, how many 3-digit numbers can be formed if only non-consecutive repetition of digits are allowed? So again, we can't use the permutation formula because there is repetition allowed. We'll use the rule of products, but we have to think a little bit about this one. Only non-consecutive repetition of digits allowed. So let's say here are my 3 places. In the first place, I can put any digit I want. So I'll say there's 5 choices for the first digit. The second place, I know that it can't be a repetition because it's consecutive. So I only have 4 choices, meaning I have whichever digits I didn't put in the first spot, those are my choices. And then for the third spot, well, now the third spot cannot match the second spot, but it could be the same as the one in the first spot. So again, there are 4 choices, but if we looked at the actual possibilities, they would be different numbers than the one in the second spot. Nonetheless, we would use the rule of products to say, well, then there's 5 times 4 is 20, times 4 is 80 different possibilities for the third question. Okay, let's work through a few exercises together. How many 3-digit numbers can be formed from the digits 1, 2, and 3 if no repetition of digits is allowed? List them. So my possible digits are 1, 2, and 3, and I want a 3-digit number. I'm not allowing any repetition, so I have 3 choices for the first spot, 2 choices for the next spot, and only 1 choice for the last spot. This is 3 factorial, or 6 choices, rather 6 3-digit numbers that we can form this way. And then it asks us to list them. So I'm going to say, well, what if I choose 1 for the first blank? Then I can have 2 and then 3, or I can have 3 and then 2. Instead, I could choose 2 for the first blank. Then I could have 1 and 3, or I could have 3 and 1. Or if I chose 3 for the first blank, then I could have 1 and 2, or I could have 2 and 1. And so I do find exactly 6 possibilities. The next part of the question is, how many 2-digit numbers can be formed if no repetition of digits is allowed? So now I have only 2 blanks. I'm not allowing repetition, so again I have 3 choices for the first blank and 2 choices for the second blank. So this is 3 factorial divided by 1 factorial. It's still 6 numbers. Then I'm asked to list them. So I'm actually going to see that I can just use the same list as above if I just consider the first 2 digits of any given number. That is to say, if I choose 1 for the first blank, then I could have 1 with 2 or 1 with 3. If I choose 2 for the first blank, then I can have 2 with 1 or 2 with 3. And if I choose 3 for the first blank, then I can have 3 with 1 or 3 with 2. So these are the 6 different 2-digit numbers. And then finally, how many 2-digit numbers can be obtained if repetition is allowed? So if repetition is allowed, still doing 2-digit numbers, I have 3 choices for the first blank, I have 3 choices for the second blank, so I have 3 squared equal to 9 numbers that can be formed this way. Okay, next question. Let A be a set with the cardinality of A equal to n. Determine the cardinality of A cubed. Now remember that this notation, when I say A cubed, I mean the Cartesian product of A and A and A. That's the thing I want to find the cardinality of. And I remember from the lecture on Cartesian products that that's just the cardinality of A times the cardinality of A times the cardinality of A, because A was of finite cardinality. So that's n times n, which is n cubed. What about the cardinality of the set of all possible triplets A, B, C, where each coordinate is different? So an element of this set is going to be a triplet. I'm going to think of it as these three blanks. The set A has n elements, so there are n choices for the first blank, but then I know that I want each coordinate to be different. So for the second, I have n minus 1 choices, and for the third, I have n minus 2 choices. So the cardinality of this set then should be n times n minus 1 times n minus 2. Another way of expressing that is n factorial divided by n minus 3 factorial, because again I know that if I wrote this out, I'd have n times n minus 1 times n minus 2 times n minus 3 dot 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 so on times 3 times 2 times 1 divided by n minus 3 times n minus 4 dot 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 times 3 times 2 times 1, and everything's going to cancel, and I'm left with n times n minus 1 times n minus 2. Next question. The state finals of a high school track meet involves 15 schools. How many ways can these schools be listed in the program? So this is just a straightforward ordering. I can use the rule of products to say, well, if I have 15 blanks, then I have 15 ways to fill the first one, 14 ways to fill the next one, 13 ways to fill the next one, and so on. And I can say that this is 15 factorial by rule of products. Or I can think of it in terms of permutations, and I could say that this is a permutation of 15 objects taken 15 at a time. And that would tell me that it's 15 factorial divided by 15 minus 15 factorial, which is 15 factorial over 0 factorial, which is 15 factorial over 1, which is 15 factorial. Now the next question is, how many ways can a gardener plant 5 different species of shrubs in a circle? So let's assume we have a circular garden, and I'm going to put 5 spots here for 5 different shrubs. How many ways can the gardener plant 5 different species? So we know that we're thinking about permutations. So I'll say I have 5 choices for the first spot, then 4 choices for the next spot, and so on. So that would give me 5 factorial. But there's something interesting that's happening now because it's a circle. So if we think about, say I have A, B, C, D, and E, or I had A, B, C, D, and E, we're going to consider these as the same because their positions relative to each other are the same. And so to account for that, I would need to divide by 5 for the 5 places. So when we have a circle, all of these permutations are the same. So we get 5 factorial over 5, which is just 4 factorial, or 24. Next, what if 2 of the shrubs are the same? So I have 5 total shrubs, but 2 of them are the same. Then again, I'm going to have my 5 factorial over 5. But then think about the 2 that are the same. I numbered one of them 1 and the other one 2. Then of these 24 permutations that I found, because the 2 shrubs are identical, some of them are actually going to be the same. Instead of calling them 1 and 2, if I took the tags off, then I can't tell them apart. Since there were 2 repeated, I'm going to also divide by 2 factorial. If I had 3 repeated, then I would divide by 3 factorial. And so this is going to end up being 4 factorial divided by 2 factorial, or 24 over 2, which is 12. And finally, what is the answer if all of the shrubs are identical? Well, if I have 5 shrubs that are all the same, then I'm going to say there's only one way to plant them all together. All right. Now let A be the set 1, 2, 3, 4. Determine the cardinality of the set of ordered pairs A1, A2 such that A1 is not equal to A2. So if I am looking at an element in the set, an element of the set is going to be of the form blank, blank. And for the first element, I have 4 choices. For the second one, I know that it's not going to be equal to the first one, so I have only 3 choices. So this is 12. The cardinality of the set is 12. Which is 4 factorial divided by 2 factorial. Now, what is the answer to the previous part if the cardinality of A is n? Then still we have an element of the set is an ordered pair, but now for the first place I have n choices, and for the next place I have n minus 1 choices. So I have n times n minus 1 is the cardinality of the set. And that's n factorial over n minus 2 factorial. Now what if the cardinality of A is n? How many m tuples? So by m tuples we mean ordered with n number of spaces. So this is m many. And m is less than or equal to n. So since the cardinality of the set is n, I have n, then n minus 1, then n minus 2, and so on. All the way down to n minus m minus 2 and n minus m minus 1. So the cardinality of this set, A1, A2, AM, so that A1 is not equal to A2, and so on. Well, this should be n times n minus 1 times n minus 2. All the way down here, I have n minus m, and distributing the minus, I'm going to write plus 2. n minus m plus 1. And that's going to be n factorial divided by n minus m factorial, which we know is exactly our permutation formula. So I can write this as p of n comma m and that does look like the conclusion of this lecture note. So we'll learn more in the next video.